Slaap Kanem. I'm going to Zor Germa Zor. Alright, hey guys, it's Coach Carroll here with a tutorial video over 2D vector addition. Okay, so we're going to look at this example problem today. So in this example problem, you have a bracket here that is fixed to the wall. Okay, and you have three forces actually pulling on this bracket. And the question asks us, it says, if the resultant force acting on the bracket is required to be a minimum, okay, determine the magnitude of F1 and the resultant force. Okay, they tell us this angle phi here is 10 degrees, that's this angle there. Okay, 10 degrees. Okay, so the resultant force, another way to say that is the net force, the total effect, the sum. Okay, so we want the sum of these three forces to be minimum, and we don't know what F1 is. Okay, so I'm going to write out the general governing equation here. And so the resultant vector is the sum of all three force vectors acting on the bracket. Okay, so don't forget, when you're writing a vector equation, you need the arrows over the variable names for the vectors to denote that they're a vector. Okay, so we just want to add vectors. Okay, so what do I know about these vectors? Well, a force is a vector, and to define a vector, you need to know two things about it. You need to know the magnitude and the direction. Okay, so for F3, I know the magnitude is 260 newtons, and I also know the direction of it based on this right triangle here. Okay, so I know everything about F3. Now F2, I know the magnitude, and I see that it's pointing in the positive x direction, so I know magnitude and direction, so I know everything about F2. Alright, now the force vector F1, as we said already, we don't know the magnitude of it. Okay, that's one thing the question asks for. But we do know the direction. We know this 10 degrees. Okay, so we don't know some of this F1. We don't know the magnitude of it. So if I need to find something about F1, well, I'm going to need to know something about this resultant vector. And the question says that they want the resultant vector to be a minimum. Okay, so that means I want the magnitude of it to be as small as possible. Okay, so you say, how do I calculate that? Okay, well, a good problem-solving method is, if you're not sure what to do, try to sketch a picture of the physics of the problem, and hopefully when you see what's going on in the picture, that will give you a better understanding of it and give you more clues on how to solve the problem. Hopefully you can see the solution. Okay, so I'm going to graphically start to sketch the addition of these three force vectors, and hopefully we'll see from the sketch how to make R a minimum. Okay, so I'm going to start with a force vector that I know in the addition process. I know F3. I should start here. Okay, so I know F3 is pointing down this way, about that length. F2 is directed over. Okay, so there's F2, here's F3. Alright, notice when I added force vector 2 to force vector 3, I started force vector 2 on the head of force vector 3 and then added it there. Okay, now some of you may be thinking, well, if I want to minimize the net force acting on the bracket, why would I even need to pull on F1? What if F1 is 0? Shouldn't that minimize it, since I'm not adding any more force to the bracket? Well, you have to remember that we're adding vectors and not adding simply magnitudes. If you're just adding magnitudes, well, maybe that's true, but we're not adding magnitudes. So if F1 is 0, so then the addition of F2 plus F3, the resultant of that, of those two vectors, is right there. We'll call that R1. Okay. But now, what if I actually add some force to F1? So I actually pull on F1. Well, again, I don't know the magnitude, but I do know the direction is pointing up this direction here. Okay, so let's say, what if F1 is this big? What if that's F1? What does the resultant look like now of all three force vectors? So F3 plus F2 plus F1, there's the resultant vector. We'll call that R2 now. Okay, so is R2, how does it relate to R1? R2. Well, R2 is less than R1. You see, it's a shorter length than R1 is, and the length of the vector represents the magnitude of it. Okay, so what if I make F1 bigger? All right, so the question is, how big do I make force vector F1 so that the resultant vector is actually a minimum? Okay, so what about this force vector? Well, sorry, this resultant. Well, this resultant is shorter than R2. That one is even shorter. Now what if it's up here? Well, now it's starting to get longer. That's even longer. Okay, so I'm drawing my resultants to meet the line of action of F1. Just from looking at this, I see that this is the shortest one here. Okay, so this is the answer for the minimum resultant vector right there. That would be the R that's a minimum. Okay, and so the force vector F1 that actually makes that resultant vector would be this force vector F1 here. Right there. So that's the answer. Okay, so hopefully we see from sketching this picture, hopefully you got a better understanding of what it means to actually make the R minimum. So I can get an approximation of the answer here. Now, obviously, I have not calculated a number. Okay, we need to do that next. But this sketching actually showed us a better understanding of the problem. Okay, so now I need to represent this picture mathematically. This is very important to be able to mathematically describe the physics of the problem. Okay, so when I add vectors mathematically, I need to divide each vector into its components and then add similar components. Okay, so we want to find the resultant vector, or we want to make it minimum, okay, by adding F1, F2, and F3. Okay, so I'm going to write each of these forces in component form so I can get a function of R. Okay, so let's write F3 in component form. I can do that. Okay, well, when I do this, I like to actually draw the components of the force vector that I'm dividing into component form, so it's easy for me to see and I make less mistakes. So here's force vector F3. So that would be the y component of it. That would be F3y. And then this would be F3x there. Okay, notice I made a right triangle with the two components. Okay, so the sum of the y component plus the x component gives me the resultant F3. Okay, so F3. If I want to get the x component, I take the magnitude, 260. Now, I need to use this right triangle here with that right angle to actually find the x component. So if I look at this triangle, I know that this leg 5 is parallel to the x-axis here. So if I use the ratio of 5 over 13, which is the length of the hypotenuse, multiply that ratio times the magnitude, and that gets me F3x here. Okay, don't forget the unit vector I hat on this component. Alright, now what about the y component? Well, we see the y component is pulling down in the negative y direction, so minus 260. Now what ratio do I use this time? Well, this time the leg 12 is parallel to the y-axis, so the ratio of 12 over 13 j hat. What are the units of this vector here? units of newtons. Don't forget units on your vectors. Okay, now let's write force vector F2 in component form. Well, this one's pretty easy. I know the magnitude of it, and I see that all of force vector F2 is in the x direction. None of it is in the y direction. So to write that in component form, it's just 200 I hat newtons. Okay. Now let's write F1 in component form. So even though I don't know the magnitude of F1, that's okay. I'm going to leave it as an unknown variable name. Call it F1. Okay. Now again, let's draw the components of F1. That would be F1y, and there's F1x. Okay. Notice I formed a right triangle here. That's the angle phi. Okay. So to get the x component, am I going to use sine or cosine of phi? Well, here's the x component, and it's opposite angle phi in my right triangle, so I'm going to use the sine of phi. And remember, phi was 10 degrees, so sine of 10 degrees I hat. So there's the x component. Now, is it positive or negative? Well, see, it's pointing back to the left, and that's the negative x direction, so don't forget your negative sign there. Okay? Now, the y direction is positive, and will I use cosine or sine this time? Well, the y component is adjacent to angle phi in the right triangle that I've made of the components, so plus F1 times the cosine of phi, which is 10 degrees j hat. And there's newtons there. Okay, so now to actually write a function for the resultant vector, and I'm saying function because I don't know F1. Okay, well, I'm going to add up all the x components, and that will be the x component of the vector, and then take the sum of all the y components, j hat, and I can add these together because they're all similar units of newtons. So for the sum of the forces in the x, I add all of the x components, and for the sum of forces in the y, I add the y components there. Okay, so I'll write that force vector here now. So R, when you do that, the x component comes out to be 300 minus F1 times sine of 10 I hat plus F1 cosine of 10 minus 240 j hat newtons. Okay, so there is the vector R. Okay, now I want to write a function of the magnitude of this now, because I want to make the magnitude of R, which is shown, you can show it like that, the magnitude of R, I want to make that minimum. Okay, so I'll write a function for R. So overall what you would do, you would square the x component, add that to the square of the y component, take the square root of that, and that's how you have the magnitude. Okay, so let's write that out to be very clear of what we're doing here. So 300 minus F1 times the sine of 10, let's square that component, and then get the y component, F1 times the cosine of 10, whoop, not a parentheses yet, minus 240, there we go, square that, so that would be Rx, and this would be Ry. So now I have a function of the magnitude of the resultant as a function of F1. Okay, so R is a function of F1, and I want to make this R minimum. Okay, so this is a great situation to plot this function and actually see if I can find where the minimum is. So when I make plots, or many times when I'm solving these problems, I use Wolfram Alpha, if you say, as my calculator. It can do it's much more than just a calculator, though. It can plot functions for you. It can find stock market statistics. It can tell you about the weather, all types of different things. Okay, so let's actually use Wolfram Alpha here to make the plots. Okay, so just to sketch this out again, I was plotting the function r, which was the square root of this 300 minus f1 times the sine of 10 squared plus f1 cosine of 10 minus 240, all that squared. Okay, so I want to take this function and put it into Wolfram alpha. So I tell Wolfram alpha just to plot. Okay, then I use SQRT to stand for the square root, so to stand for that. And now I just type out these components. Now one thing I did was I used x instead of f1. And I do that because Wolfram alpha sometimes does not like it when you use complex variable names such as f1. So I use the standard variable name as x. So in my case, x is f1 here. Okay, but other than that, you can just type out what you have here. All right, and tell it to plot it. And here was Mathematica's interpretation, or not Mathematica, sorry, Wolfram alpha's interpretation of what I told it. We can see that it interpreted it correctly. Okay, so here's the plot of this function. So what are the axes here? What's y? Well, y is actually the magnitude of the resultant vector. And what's x? Remember, x is actually f1. So where is r a minimum? Well, I can see it. It's right there. That is when r is a minimum. Okay, so what's the answer? It's about, so when f1 is about, that's about 290, then r is a minimum. Okay, so I can actually solve for that mathematically by saying, when does the slope of this line, so when does the slope of this curve actually equal 0? Okay, so what's the slope of the curve here? Slope of the curve, let's draw a line tangent to the curve. You can see it's negative. As we go from left to right, it's sloping down. What about here? I'm going to draw a line tangent to the curve. So a line tangent to the curve is the slope of the curve at that point. Okay, so I see that the slope of the curve at the very bottom, what's the slope of that line? The slope of a horizontal line is 0. Okay, so I need to say, when does the slope of this curve equal 0? And how do you find the slope of the curve? That's a derivative. Okay, so to find a derivative, when the slope equals 0, that's when the derivative of r with respect to f1, when does that equal 0? So I want to solve this equation for f1, because when the derivative equals 0, that's when the slope equals 0, and for us, that's a minimum with this function. Okay, so I can solve this equation now. So take the derivative of this function here, set it equal to 0, and solve for f1. Okay, so let's not get too worried about that. Let's have Mathematica do the work for us. So, I keep saying Mathematica. This is Wolfram alpha here. So there is my function for the resultant. Okay, so I just told it this d dx here. Let's just take all this says is take the derivative, okay, of the resultant with respect to f1, and then I want to solve that when that equals to 0. Notice that right there, when that equals to 0. Okay, so just tell it to solve that equation. That finds when the slope is equal to 0, which is a minimum, and there's the answer there. Here was what Wolfram alpha interpreted. I can see it interpreted it correctly. There's the function r right there. Take the derivative with respect to x and set it equal to 0. So when f1, that's the answer for f1. Now, what are the units of this? It's in units of newtons. Okay, so when f1 is 288.45 newtons, r is a minimum. All right, so we've got f1. If you remember, I'm going to back up here. The second part of the question asks us to find what is that resultant force then. So what is the resultant force when it's a minimum? Well, now that we have F1, it's not that hard. I just need to substitute the magnitude of F1 into the function of my resultant. So here's the function of the resultant. Okay, I just copy pasted that from my last slide, and I just tell Wolfram Alpha, hey, when x is 288.45, what is this? Okay, and there's the interpretation, and that's the answer. Okay, so this is units of newtons, and that is the resultant. That's actually the minimum R. Okay, so the minimum resultant is 253.8 newtons. All right, and that's the solution there. So to recap, okay, it's always good to look back on your problem-solving method and say, what did I do? How did I find that solution? Because at the beginning of this video, when you read this problem, you said, well, I'll just have to watch for the next 20 minutes and figure out how to do it. But now that you see how to do it, hopefully these problem-solving methods make more sense to you, and you can understand why I started actually drawing the picture here. Okay, so draw pictures is a great way to help you see and understand the problem. And remember, when you're adding vectors, just divide them into component form and add similar components. In this case, I actually had a function for the magnitude, because I didn't know the magnitude of F1. So I made a function of that. Then if I wanted to find the minimum of the function, just plot that function, which is what I did here. And then I said, well, hey, there's the answer, right? I could see the answer on this graph. I just needed to mathematically solve for that. Mathematically to solve for that, that's when the slope was equal to 0. The slope mathematically is a derivative. So I took the derivative, set it equal to 0, and got the answer. All right, guys. Hope you understand that better. Have a good day.